There are three common levels of precision used for floating point numbers. There's a single, a double, and a long double. It's the double precision format that we've been discussing in the previous lectures and that we're going to continue to focus on here. But as practical matter, everything we talk about for that format applies just as well to the others, only with the number of digits and the maximum exponent changed. So far, we spent quite a lot of time focusing on how numbers are represented internally. And that's important to do since it sets the stage for the limitations on the numbers that we can talk about. However, going forward, this is a math class, not a computer science class, so our focus is going to be on the actual numbers rather than how they're represented. So as we've seen, our double numbers can be written as a binary number starting with a 1, followed by 52 binary decimal places, that's the mantissa value in the table, times the power of 2 raised to an exponent. That exponent is an 11-digit binary number, and that's the m in the table. So a number written in this particular format is referred to as normalized, or this is the normalized version of the number. The numbers that can be represented exactly in this format are what we call machine numbers. So sometimes you'll see this normalized format rewritten so that it starts with a 0 instead of a 1. Right, so in this case, there are m plus 1 binary digits, and the first one has to be a 1. And the exponent is increased by 1 to account for the shift of the decimal point. And we can also write a decimal version of this normalized form where the individual digits can be from 0 to 9, except for the first one, which can't be 0. So what about the non-machine numbers? Well, if a number doesn't fit perfectly into our normalized format, then it has to be approximated somehow. And the notation we're going to use for this approximation of the number is FL of x, right? FL as in floating point. So there are two methods for achieving this approximation, both of which I'm sure are familiar to you. On the one hand, there's the chopping or truncating method, which just drops all of the values after the last available decimal place. Now, in general, while this method is the easier to implement, it's one that we're going to want to avoid. In the end, this method always rounds down, which can create a bias toward underestimating in our final results that we'd like to avoid. So on the other hand, there's the rounding or rounding to nearest rule that looks at the digit after the digit we're going to round to and rounds up or down based on whether or not, thinking of this in decimal terms, whether or not it's greater than or equal to 5. Now, this is the classic rounding rule that you learned, I don't know, probably all the way back in elementary school. Now, the actual IEEE rule for rounding binary numbers is a little more complicated. It starts off in a familiar way, right? By looking at that 53rd digit, that's the digit after the last one in our binary representation, and rounding down by truncating if that digit is 0, and rounding up if that 53rd digit is 1. Then there's this strange special case that says if every digit after the 53rd is 0, then don't round based on the 53rd digit. Round based on the 52nd digit instead. And I know this may sound like really weird, but it's there to prevent a more subtle version of that same rounding bias we had with the chopping case. If the digits from 53 on are 1, 0, 0, 0, 0, and so on all the way out, then the number is the same distance from the next number up and the next number down. So in this case, if we just followed our previous rule, we would again introduce a slight bias toward rounding up that this full rule is designed to avoid. At this point, some of you may have noticed that I've been speaking very blithely about the 53rd digit and a number that's only supposed to have 52. Well, the explanation for this is that the forms we've been talking about are used for storing numbers, not for manipulating or doing calculations with them. Computers have special registers for doing arithmetic operations. They can go out beyond our 52-digit limit. Then, when the calculations are done, we have to apply one of these approximation methods to round it back down to get it to within the maximum allowable size before it can actually be stored. So I want to take a quick look at an example of this process that's going to illustrate some of the challenges that we're going to run into. All right, so let's say we take a very simple number, right, 5.4. And I want to come up with the floating point approximation of this. All right, well, step number one is going to be to take this 5.4 and convert it to its binary version. Now, if you really just love doing lots and lots of repeated division, you're certainly welcome to check this by hand. I had a computer do that for me. Okay, so that's the binary version, and it goes out, and you're welcome to count them up here. This last number here is the 53rd decimal digit. Right now, before we do anything else, I want to get this into the normalized form. Right, so what I'm going to do is I need to take the decimal place, almost like you do in scientific notation. Right, I need to take this decimal place and I need to move it 2 places to the left. Now, doing that, if this were a decimal number, would increase it by would decrease it by a value of 1/100th. So I would have to multiply by 100, or 10 squared. We're doing this with binary numbers. You do the exact same thing, only instead of a power of 10 is a power of 2. Right? So when I move that decimal place, I'm going to end up with this. You notice how at the end here, I have that power of 2. And I dropped the last 2 digits. So my final digit now is that 1. Right? And that's the one that's going to determine my rounding. Now, I know that this was obviously, it's a repeating decimal, right? I know there are digits out beyond that 1 other than 0. So I'm going to use kind of the standard version of the rounding rule. And because that's a 1 there, I'm going to round everybody up, which means I'm going to add 1 to that 52nd decimal digit. When I do that, the number turns into this. So this 0, 1 here turned into 1, 0 down here. So this would be my machine number approximation of 5.4. Okay, fine. What does that mean? Well, if we take this number, and again, I did not do this myself. There was a computer program, right, that did this. If we take this number and we convert it back to a decimal number, you see where the trouble starts. The decimal equivalent of that last number there is not 5.4. It's 5.4, whole bunch of zeros, 35527. So you can see where the approximation took place. Right? Our floating point approximation is truly an approximation. It is not equal to the original number. Right, so what are some of the potential consequences of this? Well, say we try to do this. Right, 5.4 minus 5 minus 0.4. Well, as you know, a person who understands basic arithmetic, looking at that, it's pretty obvious, right? It's going to be 5, should be 5. However, that's not what a computer gets because of that approximation, right? When I asked, I actually did this in MATLAB. When I asked MATLAB what this equals, it gave me this. A really small number, well, 10 to the negative 16. That's a pretty darn small number, but definitely not 0. This is the sort of thing that can cause us headaches, especially when we start getting into the kind of repetitive calculations that we're going to be doing with a lot of the numerical techniques we're talking about in this class. Right, now, if you're curious, if you've got access to MATLAB, that actually is what I entered into the program to do these calculations. I started by defining a variable, right, equal to the original number, which of course MATLAB stored internally using that approximation technique. Then I did the subtractions. I said let y equal 5.4 minus 5, took the 5 off, and so far it's looking good, right? But then when I tried to subtract off the 0.4, yeah, that's where we ended up. And you see the problem that we had with the approximation technique. So the next lecture, we're actually going to continue with this example. And we're going to look at a couple of methods for quantifying this error that we're seeing. they're probably already going to be familiar to you. If you've taken any kind of science class, we're going to use the same idea of absolute error and relative error, exact same formulas that the science guys use. So if you're following along with the whole series, you might want to just glance at that one real quick. Maybe just skip to the second slide where I actually start to do some stuff with this particular approximation here. And then you can move right along to the next one, where we're going to start to look at the sorts of errors that can happen as a result of this approximation in more detail.